For our first example, we're going to look at this simple equation. We can solve it by first squaring both sides, subtracting everything over to one side, giving us a quadratic, which we can factor, which implies that the solutions to the equation are x equals 3 and x equals negative 2. Checking these, we're going to see something interesting happens. We see that 3 is a solution, and then plugging negative 2 in, we see that negative 2 is not a solution. What's going on here? You may have been exposed to this idea before under the name of an extraneous solution. To be a little more precise, we might refer to an extraneous solution as a solution that is introduced by the steps taken to solve your equation, but is not a solution to your original equation. Now, if you're anything like me, extraneous solutions have been the sort of thing that shows up in my math over the years in really inconsistent ways. I think probably the most common way people are introduced to it is at some point you take a unit, maybe on logarithms in school, where you learn to associate that specific unit or those couple weeks in time with extraneous solutions. And so for those just couple weeks, you develop the habit of always plugging in all your solutions that you find algebraically back into your original equation to check them. And then as soon as that unit is over, you stop checking if your solutions are extraneous. This has always bothered me a little bit because there's always the question in the back of my mind when I'm doing algebra, could some of my solutions be extraneous? Because if you're anything like me, you don't plug every single solution that you find back into your original equation. Given that, the goal of this video is to explore two questions. First, we want to understand where extraneous solutions come from. And then the hope is once we understand where they come from, we can use that knowledge to be more precise about when we check for extraneous solutions to guarantee that we don't propose as a solution to a problem a solution that is in fact extraneous. So to begin exploring this question, we're going to first take a graphical approach to this first equation. So if you can recall, if given an equation, we can visualize the solutions to that equation as the intersections of the two lines we would get by graphing the left side and the right side of the equation. And what we see here is for our first equation that if we graph the left side and the right side, we have just one solution at x equals 3 as we would expect based on the previous calculation. So now let's square both sides and see what happens. Suddenly, we have two intersections. One at x equals 3 still, but now also one at x equals negative 2. So right off the bat, this squaring step seems suspicious. And let's just follow through the rest of the algebra and see if anything else weird happens. So we can subtract to both sides, getting this. And again, we see that the two intersections are x equals 3 and x equals negative 2. And of course, factoring isn't going to change this picture. So what we can see is that in our steps of algebra, the step that introduced this extra solution was squaring.
Now that we have identified the squaring step as the source of the problem, let's plug negative 2 into the original equation and then take a look at what happens when we square both sides. In the first line, we can see, as expected, that negative 2 is not a solution. However, after squaring and doing some simplification, we end up with the true statement 2 squared equals negative 2 squared. What I want you to notice is that the extraneous solution is appearing because squaring sends two different inputs, 2 and negative 2, to the same output, 4. It turns out that this is a defining feature of algebra steps which create extraneous solutions. The proof is a bit beyond this video, so I will simply state the result. Assuming you are careful about the domain of the functions involved, extraneous solutions can only be created when you perform an operation to both sides of the equation that can send two different inputs to the same output. We call functions that never send two different inputs to the same output one-to-one. It turns out that many operations we commonly perform, such as adding or subtracting from both sides, multiplying, dividing both sides by a number, etc., are one-to-one, which explains why we so often can get away with not checking for extraneous solutions. So how can we test if a function is one-to-one? Simple. We can graph the function and apply the horizontal line test. let's quickly review that. Once we have the function graphed, we can perform the horizontal line test by imagining a horizontal line sliding down the graph. We can conclude that a function passes the horizontal line test and is one-to-one if the horizontal line never intersects the graph of the function more than once at the same time. So for example here, as I continue to let the blue line slide down, we can see that it never intersects y equals x or y equals x cubed more than once at the same time. What that tells us then is if I had an equation and I cubed both sides, I would not have the possibility of introducing an extraneous solution. Now let's take a look at the horizontal line test in the case that it fails. Sliding the line down, we can see, if we stop it right here, that it intersects the graph of y equals x squared twice. This tells us, as we expected, that x squared, the squaring function, is not one-to-one and hence can introduce extraneous solutions. As another example, if we stop the line here, we can see that it intersects the graph of sine of x many, many times. Again, telling us that the function sine of x is not one-to-one, from which we can conclude that if we had an equation and we decided to take the sine of both sides, it would be possible to introduce extraneous solutions. So, to put that all together, if we want to check whether the operation we're doing could possibly introduce extraneous solutions, we can graph it and then apply the horizontal line test to check if it's one-to-one. Let's go back to the caveat I put on the result from the last example about being careful about domains. We are now going to look at a case where an extraneous solution is introduced by operating on both sides of an equation with a one-to-one function, seemingly in contradiction to the previous result. However, we will see that this is due to an overlooked error in simplifying. To begin solving the equation, we first put both sides into the natural exponential, a one-to-one function. I encourage you to check that this natural exponential is one-to-one using the horizontal line test. Once we put both sides in the natural exponential, we can subtract everything over to one side, giving us the same quadratic as before. Factoring tells us our solutions are supposed to be -2 and 3. Plugging them back in to check, we see that 3 is a solution. And then something interesting happens when we try to plug in -2. Now remember that the natural logarithm is only defined for positive numbers. Thus, -2 cannot be a solution because we end up needing to take the natural logarithm of a negative number. So, what's going on this time? As before, let's take a look at the graphs. Graphing the first line of the equation, we see, as expected, that there's a single solution at x equals 3. Taking the natural exponential of both sides and graphing, we see that a new intersection has been introduced at x equals -2. Factoring or subtracting over to both sides, factoring, we see that the intersection stayed the same. As before, then, we can see that the suspect step is the first one, taking the natural exponential of both sides. To understand what is going on, let's be a bit more careful about writing down what we mean by taking the natural exponential of both sides. I want you to notice that when we cancel the natural logarithm out with the exponential, we are actually doing 2 steps, taking the natural exponential of both sides, as represented by the second line of algebra you see here, and then simplifying the third line. The third line of algebra will only be correct if it is true that e to the ln of x squared minus 6 is in fact equal to x squared minus 6, and if e to the ln of x is equal to x. It turns out that this is not completely true. Because the natural logarithm is only defined for numbers bigger than 0, e to the natural log of x squared minus 6 is only defined for numbers who have absolute value greater than the square root of 6. Thus, this equality can only be true for numbers whose value is bigger than the square root of 6. The same is true for e to the ln of x equals x. This equality will only be true when x is greater than 0. Thus, when we take the natural exponential of both sides of our equation before simplifying, the equation only makes sense if x is greater than the square root of 6. However, when we make the simplification and end up with the line x squared minus 6 equals x, whose domain is all numbers, we have accidentally increased the size of the domain to include negative 2, which is a solution to the equation x squared minus 6 equals x, but it doesn't even make sense to plug it in to the prior steps of the algebra. If we had tracked these domains throughout our algebra, we would end up with the statement x minus 3 times x plus 2 equals 0, but only for numbers that are bigger than the square root of 6. Of course, 3 is bigger than the square root of 6, and negative 2 is less than the square root of 6, and we would conclude correctly that 3 is the only solution. Let's return to our motivating questions and talk about what we can conclude from these two examples. From the first example, we saw that an extraneous solution can be introduced by operating on both sides of the equation with a function that is not one-to-one. Thus, we can simply conclude that we know to check for extraneous solutions if we apply a non-one-to-one function to both sides of the equation. Remember that the horizontal line test is useful to check if a function is one-to-one. From the second example, we saw that extraneous solutions can also be introduced by increasing the size of the domain through imprecise simplifying. This leads to the conclusion that we should check for extraneous solutions whenever the algebra used to solve the equation involves functions with restricted domains.